Now the first example that we're going to look at is 3 sine theta plus 1 equals 3. And we're going to find the solutions for theta that make that true between the limits of 0 and 360 degrees. Now we already know that there's likely to be two solutions to that, but let's look at how we identify those. Now the first thing that we need to do is rearrange this equation, and in order to get theta on its own, we need to strip away all of the terms that don't relate to theta. And in particular, I'm referring to this plus 1 here. So our first operation is to minus 1 from each side. Now minusing 1 from the left-hand side leaves me with 3 sine theta. And minusing 1 from the right-hand side leaves me with 2. Next, I want to isolate sine theta. So my next operation is to divide each side by 3. Now dividing the left-hand side by 3 leaves me with sine theta. And dividing the right side by 3 gives me 2/3, or 2 over 3. Now this is where things may be a little bit different from what you've seen previously, because we need to find the inverse of sine. We need to undo sine theta to leave theta on its own. And the function we use is called the inverse sine. This can be found on your calculator by pressing Shift Sine, and you'll see a function with sine to the power minus 1. That represents the inverse sine. And we're going to do that to each side of our equation. Well, taking the inverse sine of sine theta just gives us theta. And taking the inverse sine, or sine to the minus 1, of 2/3 gives us 41.8 degrees. Another important thing to note is that your calculator will need to be in degrees in order to return an answer in degrees. So make sure your calculator's in degrees mode. So we know that one value of theta that makes our formula at the top true is theta equals 41.8. But if we think back to the previous video, we know that there's likely to be more than one solution. And what I'm going to do is I'm going to sketch a function. And the function I'm going to sketch is sine theta. Because the function that I've got written there, sine theta equals 2/3, is exactly the same as our original function. Everything that I've done to the left-hand side of our original function, I've also done to the right-hand side. So sine theta is the function that I'm going to sketch. And we already know that sine theta repeats every 360 degrees. It goes from 0, we have our positive segment, and then we have our negative segment. And we have 180 degrees there. Now what we're looking for is the values of theta that give us a value of the function equal to 2/3. So up here somewhere, we have 2/3, because we know the peak value up here is 1. And we've already found that at 41.8 degrees, the value of the function is 2/3, and it's going to be somewhere around there. Now we can see from our sketch that there's going to be a second value of theta that also makes the function equal 2/3. Now by producing that sketch, we can determine what that value is going to be, because the distance from 0 to here, to our first solution, this distance here, is 41.8. So what that means is, let's just track this down, this distance here is also going to be 41.8 degrees, because what we have is a mirror image. We have a function that repeats itself. So the way that we'll find our second solution then is relatively straightforward in this case. All we need to do is do 180 degrees minus the 41.8, which equals 138.2 degrees. And that would be the value here on our x-axis or our theta line. And in order to check this, we can return to our original function, because we know that 3 sine theta plus 1 should equal 3 when theta equals 138.2 degrees. So we're going to check to make sure that equals 3. And the value I get when I run that through my calculator is 2.9 recurring, or we can round that to 3, And the reason we end up with a slight rounding error is because this value of theta here and the 41.8 was rounded. So we found our two solutions. Theta equals 41.8 and theta equals 138.2. Now in this example we're going to look at one of the reciprocal trigonometric functions, and in particular we're looking at a function involving cosec theta. Now just as a reminder, cosec theta is the same as 1 over sine theta. It's the reciprocal of sine theta. Now the first steps are exactly the same. What we want to do is to rearrange that equation to make cosec theta the subject. And the first thing we're going to do is add 6 to each side to remove this term here that doesn't contain cosec theta. So add 6 to each side gives us minus 4.5 cosec theta equals plus 6. And the next thing we're going to do is divide each side by minus 4.5 to isolate cosec theta. So divide minus 4.5 each side. Dividing the left side by minus 4.5 gives us cosec theta on its own. And dividing the right hand side gives us 6 over minus 4.5. Now I could simplify that, but I'm not going to, and you'll see why in a moment. The next observation, or the next thing that we can do, is we can replace cosec theta with 1 over sine theta. It's going to simplify things for us because we understand sine theta. We know what sine theta represents. So what we end up with, instead of cosec theta, we get 1 over sine theta. And the right hand side is going to remain the same, 6 over minus 4.5. And again, I'm going to leave it in that form for the time being. This is where it's important to understand the reciprocal function. And we've seen this in the rearranging equations tutorials. When we recip a fraction, the bottom becomes the top and the top becomes the bottom. And we can do that to both sides of our equation. Recipping both sides, so recip each side, we get the following. Well, the reciprocal of 1 over sine theta is sine theta over 1, or sine theta divided by 1. And sine theta divided by 1 is just sine theta. And our right hand side becomes, instead of 6 over minus 4.5, it becomes minus 4.5 over 6. So now we can take the inverse sine in the same way we did last time. So we're going to do sine to the minus 1 of each side, because the inverse of sine is sine to the minus 1, and we're going to get theta equals sine to the minus 1. I'm going to leave this as a fraction, I could always simplify it, of minus 4.5 over 6, which equals minus 48.6 degrees. Okay, so what we've shown there is that one solution to this function, cosec theta equals 6 over minus 4.5, equals minus 48.6. The problem there is that we're looking for all solutions between theta equals 0 and 360 degrees. And obviously minus 48.6 degrees doesn't fit in that range. So we're going to do a couple of things. First of all, we're going to rewrite this formula. And we're going to rewrite it as follows. Cosec theta, the left-hand side is going to remain the same, but the right-hand side we're going to simplify. And 6 over minus 4.5 is exactly the same as minus 6 over 4.5. It doesn't matter where that minus sign sits. And the value of that is minus 1.3 recurring. All I've done is simplify that. Cosec theta equals 6 over minus 4.5. is exactly the same as cosec theta equals minus 1.3 recurring. Now the next thing I'm going to do is sketch the function cosec theta. And I'm going to sketch it as we saw in the previous video between theta equals 180 and theta equals 360, because that's where we're looking for our solutions. And hopefully you recall that the cosec function, or 1 over the sine function, the reciprocal of the sine function, appears something like this, where we have minus 1 at that peak and 1 at that peak. Now the useful thing to remember is that this is a cycle, it repeats. So if we go to minus 180, then what we're going to have is a repeating of that cycle. Now we've found one solution that says the function cosec theta down here equals minus 1.33, so around here somewhere, when theta equals minus 48.6. So let's mark this on in a different colour. There's our solution, and our value of theta there is minus 48.6. Now here's the important thing. We know that this distance here is 48.6 as a distance. Now if we project this line across, we're looking for a couple more general solutions. We have a solution here. Now although this isn't to scale, the distance from 360 back to that point is also going to be 48.6 degrees. And the other thing we know is that this solution here is going to be 48.6 degrees from the 180. We're imagining that there's a mirror image line here that's mirroring that function. So 48.6 degrees from the 360 degrees point, but also 48.6 degrees from the 180 degree point. So now let's find our actual solutions of theta that sit in our range. We have one value of theta, which is going to be 180 plus 48.6. We can see that from our sketch there. And 180 plus 48.6 is 228.6. And our second value of theta, sitting in that range, is 360 degrees minus 48.6, which equals 311.4 degrees. So there we have our two solutions to the original function, minus 4.5 cosec theta minus 6 equals 0, between the limits of 0 and 360 degrees. So let's clear a little bit of space and then check those two solutions for accuracy. And the way that I'm going to check those two values is by returning to my original function, minus 4.5 cosec theta minus 6 equals 0. Now recall that cosec theta is exactly the same as 1 over sine theta. So in actual fact what we have here is minus 4.5 over sine theta minus 6 equals 0. Now we're checking that that's true for our two values of theta. So let's check minus 4.5 over sine 228.6 degrees first of all. That's our first solution that we found. Minus 6. And running that through the calculator gives 0, as we would expect, give or take a little rounding. So we know that that value there is correct. And let's check for our second value, minus 4.5 over sine 311.4 degrees minus 6 equals, and running that through our calculator gives us, again, give or take rounding, 0. So we know that that value of theta is also accurate. Now let's look at one final example. And this time we're introducing a phase shift. Now the steps are exactly the same. What we want to do first of all is rearrange that equation. And the first thing we need to do this time is divide each side by 2.5. This time we're trying to isolate sec theta plus 10 degrees. And that's going to give us sec theta plus 10 degrees equals 6.5 over 2.5. Once again, I'm going to leave that as a fraction for the time being. And the reason I'm going to leave it as a fraction is because I can rewrite that. Recall that sec is the same as 1 over cos. So sec theta plus 10 is the same as 1 over cos theta plus 10. We need to keep that bracket intact, like so. So now I have 1 over cos theta plus 10 degrees equals 6.5 over 2.5. Now here's where our reciprocal function comes in useful again, because I'm going to recip each side, each of those fractions. The top's going to become the bottom and the bottom's going to become the top. So the left hand side here is going to become cos theta plus 10 degrees divided by 1. Well, because we're dividing by 1, it's just going to be cos theta plus 10 degrees. And my right hand side is going to become 2.5 over 6.5. So now let's simplify that and we get cos theta plus 10 equals 2.5 over 6.5, which is 0.385. And doing the inverse cos of each sine, so cos to the minus 1 each side is going to give us theta plus 10 degrees equals cos to the minus 1 of 0.385. Therefore, theta plus 10 degrees equals 67.4 degrees. And finally, that means that theta must equal, subtracting 10 degrees from each side, it must equal 57.4 degrees. But to find our second solution, let's sketch cos theta. Cos theta, we have 180 degrees, we have 360 degrees, and cos theta starts at 1, goes to minus 1, and goes back to 1 at 360 degrees. So we have 1 there, we have minus 1 there. Now before we applied the phase shift, we had this solution here, theta plus 10 degrees equals 67.4. And so we're somewhere in here. This distance here is 67.4. Now before we apply the phase shift, we can use that to determine the equivalent distance from 360 degrees. Remember that we've got a mirror image here. So this equivalent distance here is also 67.4 degrees. When we apply the phase shift, the graph moves 10 this way, because a phase angle of plus leads to a shifting from right to left. And we can see that indicated in our answer, because our true value of theta after we apply the phase shift is 57.4. If we imagine all of this sliding 10 this way, so this point here is sliding 10 this way, and this point here is sliding 10 this way, then that will help us to get our general solutions. Before the phase shift is applied, this point here is 360 minus 67.4. But for our general solution to the original formula, we need to subtract an additional 10 degrees from that to accommodate our phase shift. So our second value of theta equals 360 minus this deviation here before we applied the phase shift, 67.4, minus the 10 degrees to allow for the fact that the graph is being shifted from right to left. Remember, we're using the graph here to establish our second value, and that gives us the following. 360 minus 67.4 minus 10 equals 282.6 degrees. Now it's important to check these two answers, so let's clear some space again, and we're going to check against our original function. So our original function was 2.5 sec theta plus 10, but sec theta plus 10 is the same as 1 over cos theta plus 10. So we're going to rewrite that, 2.5 over cos theta plus 10 degrees and we're trying to show that that equals 6.5. Our two values then, first of all, we're going to check our 57.4 degrees. And running that through our calculators, we've got 2.5 over cos 67.4. And that comes out to be 6.5, taking into account a small amount of rounding. So we know that that value is correct. Now let's try our second value. We have 2.5 over cos 282.6 plus 10 degrees. And when we run that through our calculators, 2.5 over cos 292.6 this time. Once again, we get a value of 6.5. So we've established our two values of theta between 0 and 360 degrees to be 57.4 and 282.6. Without sketching the graphs here, this process is made much more difficult. So it's important to produce your sketch, and once you've produced your sketch, you can then use it to help determine your solutions. We could alternatively have sketched sec x here, so we have some options, but all we're using the graph for there is to establish our second values of theta.